Look up at the night sky. What do you see? If you're lucky enough to be away from city lights, you'll be greeted by a dazzling array of stars. These twinkling points of light have captivated humanity for millennia. They have inspired countless myths, legends, and scientific inquiries. But stars are more than just pretty lights in the sky. They are the building blocks of galaxies, the crucibles where elements are forged, and the engines that drive the evolution of the universe. Stars are giant balls of hot gas, primarily hydrogen and helium. They generate energy through nuclear fusion at their cores, where immense pressure and temperature fuse hydrogen atoms into helium, releasing tremendous energy in the process. This energy makes its way to the surface of the star, where it is radiated out into space as light and heat. The color of a star is determined by its temperature, with hotter stars appearing blue-white and cooler stars appearing red. Our own sun is a star, a rather average one at that. It provides the light and heat necessary for life on Earth. By studying the sun, we can learn a great deal about the nature of stars in general. But the sun is just one of billions of stars in our Milky Way galaxy. And the Milky Way is just one of billions of galaxies in the observable universe, each containing billions upon billions of stars. The sheer number of stars in the universe is mind-boggling. But each of these stars, from the smallest red dwarf to the largest blue supergiant, follows a similar life cycle. Understanding this life cycle allows us to trace the history of the universe and appreciate the interconnectedness of everything in the cosmos. Stars are born in vast, cold clouds of gas and dust called nebulae. These nebulae are scattered throughout galaxies and can be light years across. Gravity is the driving force behind star formation. Within these nebulae, regions of slightly higher density begin to attract surrounding material. As more gas and dust clump together, the gravitational pull strengthens and the core of the collapsing cloud heats up. This dense, hot core is called a protostar. The protostar continues to gather material from the surrounding nebula, increasing its mass and temperature. The process of a nebula collapsing into a protostar can take thousands or even millions of years. During this time, the protostar is not yet a true star. It doesn't generate energy through nuclear fusion. Instead, it shines from the heat generated by the gravitational collapse of the material falling onto it. As the protostar continues to accrete material, its core temperature and pressure increase. Eventually, the core becomes so hot and dense that nuclear fusion begins. Hydrogen atoms are forced together, forming helium and releasing a tremendous amount of energy. At this point, the protostar officially becomes a star. Once nuclear fusion ignites in the core of a star, it enters what is known as the main sequence. This is the longest and most stable stage of a star's life. During this stage, the star exists in a state of hydrostatic equilibrium. This means that the outward pressure from the nuclear reactions in the core balances the inward pull of gravity. The main sequence is not a static phase. As the star fuses hydrogen into helium in its core, the composition of the core slowly changes. This change impacts the star's temperature, luminosity, and size. Our Sun, for example, is about halfway through its main sequence lifetime, which is estimated to last about 10 billion years. The length of time a star spends on the main sequence depends primarily on its mass. Massive stars burn through their hydrogen fuel much faster than smaller stars. This is because the increased mass creates higher core temperatures and pressures, leading to a much faster rate of nuclear fusion. While our Sun will spend billions of years on the main sequence, a star 10 times more massive might only spend a few million years in this stable phase. Conversely, a star with half the mass of the Sun could live for tens of billions of years. Eventually, every star runs out of hydrogen fuel in its core. When this happens, the outward pressure from nuclear fusion lessens, and the core begins to contract under the relentless pull of gravity. This contraction causes the core to heat up even further. The increased heat from the contracting core starts to heat up the layers of hydrogen surrounding the core. Eventually, these outer layers become hot enough for hydrogen fusion to begin in a shell around the now inert helium core. The energy released from this shell burning pushes the outer layers of the star outward, causing it to expand dramatically. As the star expands, its surface cools, causing it to turn red. This is why these aging stars are called red giants. Red giants are much larger and brighter than their main sequence counterparts, but their surfaces are significantly cooler. The fate of a red giant depends on its mass. Lower mass stars like our Sun will eventually shed their outer layers, forming a planetary nebula. The exposed core will remain as a white dwarf. However, more massive stars experience a more dramatic end to their red giant phase, culminating in a spectacular supernova explosion.